Let's get it started. Hello everybody, thanks for coming, committee and audiences. Today I'm going to talk about mid-level representation for video recognition. So let me kick off the talk by introducing the concept of mid-level representation for the task of video recognition. Suppose we have this complex scene. And we took a shot out of it, and this is the captured image. So the question is, what is video recognition? Video recognition is to take a complex scene like this and really understand what's going on here. The first step of recognition is detection, so answering to the question, what objects are present in the scene and where they are. But if you want to know more about what's happening here, you probably need to know more than where the objects are present. So you might want to ask, what are the pose of objects? The people, the animal, where they're moving toward, which is answered in tracking, and what's going on here in terms of actions, which is answered in behavior understanding. Right. So, and this is what my thesis is about: visual recognition. Try to extract all information as we can from images and videos. Today in this talk, I want to primarily focus on object detection in still images, and then go beyond the static image and try to capture the temporal information which is available actually in video sequences and understand what is the activity of people in the video. So for each image captured from a complex scene like this, we have a very huge semantic gap in between. There are different methods come up with different solutions for filling this gap by injecting semantic in terms of representation. So one might want to represent the scene, an image, using a set of interest points selected on. Another one might want to represent that scene using the set of objects consists of, but we are here, something in between. We specifically believe using mid-level representation can provide us with both low-level visual cues and high-level scene semantics. And this is the general idea behind the mid-level representation. So first, object detection. The question in object detection is what objects are where. So the goal of object detection is to train a statistical model using a set of images and a level of supervision, and in a test time we want to localize a bounding box around the objects. So for example, in this case, these are the object categories: person, cat, and dog, and so forth, and these are the bounding boxes around the objects. Of course, this problem is very challenging because we have variation in terms of lightening, pose, viewpoint, shape, and so on. It's also very competitive. It's very challenging because we have occlusion and clutter, which makes the problem even more difficult. But the main challenge to me is huge interclass diversity in terms of visual appearance. For example, these are all examples belong to the horse category, but they are very different visually because they're captured in different lightening setup, occlusion, patterns, and viewpoints. To tackle this problem, I did two different projects, so we proposed two different methods: what is supervised mid-level patches and subcategory based on weighted descent bias, both based on the concept of subcategory. So what is subcategory? The subcategory idea says that if we have an object category with a huge visual diversity, like in this case horse, we can divide the positive examples to a set of clusters or subcategories, and then we can train, we can solve this smaller sub-problems instead of solving the complex original problem, right? So for example, in this case, these are different subcategories we discovered for the horse category. This solution is very efficient because we just have some locally linear classifiers instead of the non-linear original classifier. And it's also interpretable, which means we have interpretation about the concept of each subcategory. For example, this subcategory belongs to the side view horse, and this subcategory belongs to the head of the horse. Okay? So, but the matter is, what is the good criteria for subcategorization? Different methods came up with different solutions for subcategorization, starting from viewpoint, pose, semantic, and so on. But most of the previous method was based on human supervision, which is very costly because we need to occur a human experiment to annotate the data. But in this thesis, we employed web supervision, which is available on internet for free. So this is the pipeline we use for webly supervised subcategory discovery. For a given concept like horse, we search our Google Books, which is a huge corpus available on the internet, to discover a set of n-grams. In this case, these are the n-grams, 2 grams. So then for each n-gram, we search our Google, Yahoo, and Bing search engines to download a set of images. For example, these are the retrieved images for the n-gram eating horse. But of course, not all of these n-grams are useful, so some of them are not visually at all. So we remove some part of them which are not visual, and just keep the one which is visual subcategory. We use the image level classifier for this purpose. We also have the visual synonyms, which means 2 visual subcategory which has the same similar visual appearance. So we mix them using a graph-based method. And at the end, for each visual super n-gram, we train a detector, which, as explained in this paper and the thesis. So these are the subcategories of ImageNet, which shown in each box. As you can see in each box, the examples are not so visually consistent. If you stack them all together, they are not that much spatially aligned. So, but here, these are the subcategories we discovered. As you see, in each box, which shown one visual subcategory, we have examples similar to each other. So in second step, for each subcategory, and all examples belong to the subcategory, we randomly select a set of patches inside the bounding box of the object, which is discovered by the previous step. So, and for each of these bounding box, we capture the relative position of the patch to the bounding box, as well as training an impedance model for that patch model. Right? And these are the initial patch model we train. But of course, not all of them are not useful, because some of them are not representative for that subcategory, and some of them are not discriminating. So we remove some part of them and just keep the one which is representative and discriminating. We propose the criteria for this part. Okay. And these are the final set of selected patches. After removing some noisy images downloaded from the internet, we retrain again using an accurate and fast, efficient method. And the final step is calibration of different hash models within S2. So of course, I didn't go to the detail of each step for the sake of time, but you can find more details. These are some qualitative results. These are the hypothesis bounding box of the object, and this is the final detection. The last line shows the false detection. They're still similar. They belong to the co-category, which is similar to the horse theory. We also evaluate our method quantitatively. So this is the precision recall curve. This diameter in diagonal, this diagram shows as much as we go to this direction, the results are better. This is the result. The blue curve shows the result of random patch selection. This is when we add the representative measure for selecting patch. This is when we add discrimination. This is the state-of-art method, which we call it webly supervised different-part model. And this is where when we add the patch model to the previous one. So, and this 4 or 5% improvement is as a result of adding patch model with minimal representation. So, and this is the result when we do retraining and so on. In the second project, we take advantage of presence of multiple data set for object recognition. So, and the general idea behind the work is we would like to share information across the data set in terms of sharing the statistical power available in each subcategory. Right. So there are 2 different types of sharing across data set. One is sample sharing, which means that we borrow example or transfer example from one data set to another data set, especially to the data set which the number of examples inside, subcategory with the number of examples inside is not enough for the sake of generalization. And there's also parameter sharing, which means sharing parameter of models across data set. We follow the second. So having this idea in mind, we did an experiment. We took 4 different data sets and we trained a subcategory model for each of them separately for the task of person detection. And this is the performance of the system. Then we mixed and combined these 4 data sets, and we retrained again the subcategory model. And we observed a drop in performance. That was strange. Right? But this effect has been also reported in this paper before, and known as dataset bias. We employed the subcategory idea and introduced the regularized multitask learning framework for tackling the dataset bias problem. More specifically, we jointly trained the subcategory model as well as visual word model. The evaluate method and comparative method compares to the concatenation dataset, and we show improvement in most of the dataset and for most of the categories. Also, we had the average improvement of 8.5 when we compare with the concatenation dataset, an average improvement of 6.5 when we compare with the set of art method. In the second part of the talk, I want to focus on the human behavior understanding. I also did 2 different experiments for this task. The first experiment was the first project was group activity analysis, detection and recognition of collective activities. This problem is also very challenging because we have clutter, we have occlusion, dynamic scene, we have camera viewpoint change, and so on. We introduced temporal poselet for this purpose, which the general idea behind is exploiting the dynamic of change of detector over time. In this case, we use poselet, and what you see here is the activation pattern of 3 different poselets activated in a couple of frames in the video. For this purpose, we concatenated the activated poselet along the video sequences and created the temporal poselet. We tested this temporal poselet for 2 different tasks. Group detection. For group detection, we use the sum over the value of temporal poselet as a saliency measure. And what you see here is the qualitative results of the detection. As you can see here, this is our method and this is the baseline method. We are more consistent for localizing where the people are or the source of activities. We also experimented for collective activity recognition. After removing some temporal poselet, we created a bag of word model out of it, and we trained in 1 sphere for each category. And this is the confusion matrix. As much as we are higher in this diameter of this matrix, it shows that the better is better. So this is our method, and this is the set of our method. In the second project, I did human behavior understanding, but for a more complex scenario, where the scene is more crowded and the resolution is lower, which is a typical case of video simulation. For this purpose, we use the tracklet, which is a mid-level representation between low-level optical flow and high-level long trajectory. We believe tracklets can capture both local motion information and global scene structure. For each video, we extract the tracklet from it, and then we represent it using efficient binary code. We represent it. We compute commotion measure as a measure of crowd motion, which is nothing but a weighted irregularity for motions in each video related to the dominant motion. We experimented for 3 different tasks. Pixel level, which we try to model a spatial abnormality. We tested on a couple of data sets, and these are some qualitative results. This heat map shows that the warmer color shows that where the abnormality is. We also tested for a frame level, which is trying to capture temporal abnormality. And this is our method compared to a set of art method and the graph. In video level, we try to use our method as for localizing, for capturing spatial temporal abnormality, and we use it for feature detection. We are still higher. Okay. In conclusion, we work on 2 different tasks of feature recognition. Object detection is still image, and human behavior understanding. We did 4 different projects. With the supervised discriminating patch, subcategory based undoing bias, and temporal poselet, and tracklet based commotion. In future, I would like to work on each of this part as well as combining them for creating a better visual recognition system. And these are the paper I worked on this 3 years. And I would like to thank my advisor, Vittorio Guarino, for his support during these 3 years, and all PABIS members who, if I want to mention their name, it would be a talk itself. And but specifically, I would like to thank Alessio and Alessandro for their support for at least for the publications. And the external collaborators, Santosh Anale from University of Washington for my visit here, my visit internship in University of Washington, and Masaniana.
Thank you. There are questions from the Commission?
Thank you, Moin, for the nice presentation. I have a question regarding the subcategories. You split down your data sets actually to have better classification somehow, better representation of it. I understand that you can, afterwards, you can understand more what you have in your head. Have you tried to use non-linear models to compare with actually? Because I guess you tried with linear SVMs, right?
All right.
Have you tried with some?
Yeah, that's a very good question. I think we are still below the non-linear classifiers because there are some problems because of the higher visible dimension in non-linear classifiers. We might get worse results, but the subcategory idea says that using a couple of linear classifiers can work in parallel with the non-linear classifiers, but we have also interpretability, right? So there's no proof that shows that linear classifiers, I mean, at least in the case of unsupervised visual subcategory, that non-linear classifiers collectively can work as good as non-linear classifiers. There's no proof behind that, but there are also experiments. There's no paper shows that. Yeah, it's something can be discovered later.
And another question: have you compared your tracklet, the temporal causelets actually, with motion flow actually to see? Because actually the impression that I had was that your motion flow was good for solving this kind of problems.
Well, what is interesting about temporal causelet is that we have semantic alignment with the motion, which says that